Yep, let's start. Hello, welcome everyone. Welcome to the 19 sharing sessions for Concrete Matters. Today we'll be talking about materials, which is clay. So we'd like to do a very brief introductions of today's topic and also, oh, wow, need to mute you, Reference. Yeah, and today's speakers, today we are very honored to have Jin Ting and Mehdi. So let's start with Jin Ting. Jin Ting is a very good friend of mine in the Singapore office, and then she's also an ex-colleague of mine. So her final year, so she's a master graduate from National Universities of Singapore, and then her final year project, Clay Settlement, has won the PAM Silver Award Student Award in 2020. So she'll be later sharing her final year project, and then followed by Mehdi coming all the way from US, Texas. So he's an architect with over 8 years of experience and with a particular interest in technology. And he's also a master graduate from Shiraz University and also currently a PhD student in Texas A&M University, focusing on robotic additive manufacturing and robotic fabrication in architecture. So he will be sharing with us his research and also some of the process behind. So very looking forward. So without further ado, we'd like to invite Jing Ting to share her project. So the stage is yours, Jing Ting.
Okay, I'll share my screen now.
Mm.
Hi everyone. Tonight I'll be presenting my thesis project which I have done in 2018, 2019 in NUS. So yeah, my project title is the clay settlement. So when I was in year three of my architecture school, actually I got the chance to like learn pottery. And the time I was really like amazed by the plasticity and also the texture of clay. And of course, like clay itself is a very emotional material for me also. And the process of like making such a soft material into like a very strong hard material in the end, it also it makes me feel like it's really interesting. So when I'm in year five, the time to explore my thesis, I started to look into clay in architecture. So these three are actually those projects that really like inspired me a lot during that process. So the first image is the South Asian Human Rights Documentation Center in India, and then also the Serpentine Pavilion 2018 by Frida Escobedo, and of course like Ningbo History Museum by Wang Shu in China. So yeah, it's like kind of sparks the kind of idea in me like to think how clay actually can be different in architecture. So just a short like intro about my project. Um, the project actually began with the interest in clay, like what I've mentioned, and the project actually seeks for some like innovative ways to turn the ancient material into new clay products that works beyond the conventional clay building materials. For example, like the bricks and or ceramics cladding that on the building that we can see nowadays. So I'm also of looking at clay as a material in Singapore's context. And I found out that actually Singapore has been looking for new alternative construction material to reduce the reliance of like importing raw materials from the neighboring country because Singapore is quite a small country, so it always has to like import some raw materials from some other country to for the construction industry. And then I feel that clay actually has the potential to be the new alternative because Singapore has produced like quite abundant amount of excavated soil due to the extensive underground developments, whereas only 50% of the excavated soil was reused in based on the statistic in 2011. So actually the government is also quite encouraging and called for innovative ways to recycle this excavated soil into some useful construction material. And then the next step, I was like looking for a site in the Singapore. So I came to know that this part which called Jurong in Singapore is actually quite well known for its pottery and brick industry in the early 20th century. So the factories, they are actually using this dragon kiln, which you can see in this photo at the bottom, which is like a quite a traditional way to fire their kiln, to fire the clay materials and the potteries. However, it's quite sad that in 1990s, many dragon kilns was demolished to make way for the urban development, and it only left two remaining dragon kilns, which is the Taoguang Dragon Kiln, which is the kiln in this photo, and also the other Jalan Bahar Clay Studio kiln in the same site. So these are some photos of the dragon kiln. So basically, this dragon kiln is like quite a long kiln, which is made of bricks. And then when you walk in, right, you actually can see like quite a long tunnel. And then this is actually where they will put the their pottery and their pottery in like they stack into um on the rack, like the photo on the left. And then these are some photos for the how does the kiln looks like from the exterior. And one quite interesting thing that caught my eye is that actually it has this chimney at the back of the kiln, which is on the photo on the right. So this is like a study of the dragon kiln itself lah. And how it actually works is that they will actually load the pottery into the kiln, and then they will put like a timber for combustion from the front, the mouth of the dragon kiln, and then they will actually fire for about 2 days for the material for the pottery to be fully fired. So today, Takwang Pottery Jungle is actually serving as an educational site by providing pottery classes and also like giving tours to visitors. It only fires about 2 to 3 times per year, and it also opened up for artists to fire their own pottery. So always like alongside with this the firing of dragon kill, there's also this like festival which we've held with public workshop or demonstrations and also like tea sessions. So it's actually like quite a celebrative like moments, especially you can see in this photo. It's like an event that will bring people that loves pottery around to hear to bring their own pottery to fire here, and also just to witness the firing of dragon kiln that only takes place like two times in a year. But however, the dragon kilns are actually like facing the uncertainty of being demolished to make way for the new clean tech park, which is you can see in this photo. This entire green patch over here is actually the a site for a clean tech park, which is like a eco business park in Singapore. So actually nobody really like know whether the Taoguang Pottery Jungle and also the other dragon kiln will be kept for the future, or will just like make way for the new business park in the future. So this is actually the current site at where the dragon kilns are. It's actually a very serene area. It's quite a pity to make it into a business park. As you can see on the right, there is like this red roof building. Is where the Taoguang Pottery and the Taoguang Dragon Kiln is. And also this like building on the left, like is at the small corner lah. But yeah, it's actually where the second Dragon Kiln is. So that my thesis statement will be the thesis actually seeks for innovative use of clay to create a new clay product that works beyond the existing clay molding materials. And then it will be used to create pavilion. New clay product will then be used to recreate pavilions in the master plan. And this master plan will actually take place at where the last two dragon kilns are. It also serves as a strategy to rejuvenate the current dragon kiln site and preserve the historical artifact from demolition. So my vision for this place, it will be like a hub for people to learn and create pottery art in a garden setting and at the same time integrate with the surrounding as a green sanctuary within the eco business park. So some parameters for the new clay products that I wish to like introduce is it has to control sunlight, which is provide shade for people, and also allow natural air ventilation because it's like in a park setting. Yeah, and it has to also prevent rainwater penetration because like we are in like a tropical weather. It has to work in a tropical weather, and lastly, it also has to be structural self-supporting to work as a basic building material. So I had some research about like to understand clay. Um, a few important properties about ceramics to highlight is that ceramics are generally high in compression strength, but weak in tensile forces. And secondly, ceramics are vulnerable to crack. And the process of designing with clay should also avoid like areas of high stress concentration, which will include like drastic change in thickness or sharp edges or openings. So in terms of its industrial production process, it actually means like how clay materials are actually produced in like most common like the common clay industrial process. So the first will be there will be pressing or means like the clay will be pressed in the mold to form a certain shape, and also it can be extrusion, which is sort of one of the example that is done by Renzo Piano is like quite nicely done, and is using the extrusion process to create this like repetitive ceramics structure or ceramics facade materials on the facade. And also it can be casted into a mold, and then after that you just remove the mold and you just get a pottery. Yeah. So in craft-based production, which is like widely known as like is what we can commonly see like how we make pottery with hand. It will be like the first step will always like start with wedging the clay. It's like conditioning the clay into like a more plastic state to start with. And then there are a few techniques to like make pottery. Like you can just basically play it like a play-doh, like hand building, or you can put it on the wheel to throw it to create like a more circular shape kind of vessel. And then the next step we'll need to air dry the clay, and then we'll base firing and glazing, and then we'll also fire it after we glaze it, and then will be the final product. Yeah. So after all this like more like a theoretical research, so I have started with some experiment. So the first and the actually I was using this slip casting experiment to understand this workability of clay. So I was like taking this idea of a hollow brick first. So the the mold that I was using is this like a PVC multi-parts mold that is like made by a CNC process. So after like I screw them together, I poured the clay liquid into the mold, and then I will lock the opening and by screwing the lid, and then unscrew and then just like open, and then it's like this final product that I got. For this clay slip that I was using is the non-firing kind of clay slip. It wasn't the more conventional kind of like clay that I was using. Yeah, it's like a powderish, then with add with water, and then you be pour into the clay and into the mold. So some analysis about this model is that the number of removable molds is actually quite crucial in making such a complex geometry, and also the geometry of the design. So if the design has like deep and sharp turning point, it's actually very hard to remove from the mold itself. So these are just like some points that I was thinking to remember when I was need to move on to the design stage.
Sorry to interrupt. You're saying that if there is a sharp edge in the clay, it will chip off, is it, when you remove it
This
from the
is
mold?
what happened at the photo there you see in the right corner.
Ah, okay.
Yeah.
I see. Okay, thank you.
So next, I'll be presenting the overall master plan, following by the individual pavilions and the clay cell that I've designed to make up the pavilions. So the master plan, like clay settlement, is actually a garden for public to learn and experience pottery art in a natural setting. A public learning trail is introduced as the main spine of the master plan. So as you can see, it's like quite yeah, a strong how to say, this main spine in the center of the master plan is actually the trail that leads people from one station to the other to experience like different learning journey in learning pottery and then clay as material. And then this trail is sheltered by Dragon Pavilion. It's a continuous pavilion that encapsulates the two dragon kilns, which you can see on the upper part and the sorry, it's near the number 3 and number 12 of the master plan. And also their like outdoor amphitheater, pottery learning bridge, and also the existing main entrance is also incorporated into the master plan. So around the Dragon Pavilion, Sculpture Pavilion, and Pottery Pavilion is also like placed as a satellite pavilion that is connected to this main circulation. There are also like spaces such as mud pool, sculpture garden, and clay playground, which is to support the clay related program of the site. And then in terms of ecological aspect, because the site from the site photo we can see that there's actually a very rich kind of very rich nature element in the site. There's also something that I wish to preserve. So the existing lake, the quarry lake, which you can see as the blue color portion in the plan, and also the existing biotope gardens are also retained to with a new garden water to further enhance the performance of the garden as the green lung of this like future green tech park. So let's take a closer look at the Dragon Pavilion. So the pavilion is actually designed as a sculptural landscape element that intertwine with the existing landscape and framing the scenic waterfront. It is made up of the dragon scale cell, which will be explained further in the next slide. And this pavilion actually reminds the visitor of the story of the dragon on site, like dragon kill and then like dragon, yeah. And it also functionally protects visitor from the sun and rain while bringing the visitors from one node to the other. So these are the process of like exploring how does this dragon scale comes from. So it started with like a basic geometry of a dragon scale, and then after that I'm exploring by using this stacking technique to stack them together, and then to study like some um, difference in the cell size and also the porosity. And then next, I also looking at the opening angles and the porosity, and also did some modification for like to open it to create openings for the visual connections, and also to enhance the structural integration by introducing like a diagrid structural like a diagrid kind of system to it instead of just like 90-degree stacking, and also will be incorporate with some structural reinforcement along this diagrid system. So this yeah, these are those like exploration, like possible combination of the different kind of cell that stacks together. So I also did this like 3D printed model to study like the shadow and the porosity of the dragon scale model. But unfortunately, in Singapore, I was like unable to find a clay 3D print uh printer service or any 3D print clay print. I mean clay 3D print printer. So that's why I was like using this normal kind of plastic to just like explore the shape and also explore the tectonics of it. So the next area that we are going to will be the clay amphitheater. So it actually looks like a tail of a dragon that sweeps like towards the quarry lake of the park, and then it creates this kind of like a sitting area for people to enjoy after like they have take a stroll in the garden. And also it will have a stage that actually for the pottery event, like the firing of dragon kiln, and then it will have the stage. It could be showcasing like how pottery artists they make big um sculptures in clay. And so it serves like a chance for people to actually see how pottery artists works. So the next area that we'll be going through is the Pottery Bridge. So while the Dragon Pavilion reaches the existing waterfront, it will enlarge and open up to the water body to form like a pottery workshop that floats on the existing river. So the pavilion will frame the scenic view of the river while offering a conducive pottery learning experience surrounded by the nature. And not to forget the legendary dragon kiln. So it will be preserved and then it will be sheltered under a pair of vaulted pavilion constructed by the dragon scale bricks. So the form it will reminisce the arch chamber of the dragon kiln inside, which we'll see in the photo just now. Then it also will be the main venue for the firing ceremony of the dragon kiln. And long awaited by ceramic artists and pottery enthusiasts, it will be also the time to fire their artwork by the ancient wood firing and witness the legendary kiln to come alive again. So this pavilion also actually live like also how to say accommodate for this interesting chimney that I was like quite amazed on the side. Yeah. So the next pavilion that I'm talking about will be the Pottery Pavilion. The cell that I'll be using to create this pavilion will be called the rain spout. So it is a cell that's designed with a rain repelling property, which will channel the rainwater to the exterior and prevent it from penetrating into the interior space. So this pavilion is a working and exhibition space for the ceramics artists. The design has started with the basic geometry of curved planes, which remind people of curved clay tiles. So the curved planes will recombine and stick to achieve a form that allows the cell to be self-support. And also in order to channel the rainwater, the form of cell is further modified to become like a spout shape. And then in order to like explore different porosity and also the sunlight amount that is going into the space, the width of the cell opening and the spout angle will be explored and to like adjusted to create this different porosity. So in total, there are actually 5 different cells with different opening sizes to created to offer this different level of porosity. So I also did like a water test on Diva to really like see whether it has the property of preventing water to go into the space. So in the 4 screenshot that you see on the corner, it actually works as like a rain repelling screen. So these are some of the models that I've done. So in the Pottery Pavilion, the rain sprout cells can protect the working space at the second floor and also prevent prevent the water from going in by channeling the rainwater into like a central pool. So apart from this weather performance, the cell also celebrates the beauty of the rain and the water by allowing the water to flow down the screen, and it's kind of like a water feature when it's raining. So like instead of like rain and then you got stuck in the garden, I feel like it's quite a poetic things to actually create by using the chance to create like a water feature. So the next pavilion that we're talking about is the sculpture pavilion. The style for the sculpture pavilion is actually inspired by the Van block, and this new topology of Van block actually explores a new geometry and expression by integrating curved surface within a block. So curved surface is able to help to diffuse direct light into the interior space. And also the degree of curvature also export to control the amount of light entering the space and while creating dramatic light and shadow effect. So started with like a curved surface, and I was exploring how to how to form a block from there, and actually to see after stacking them up, how is the shadows and also the amount of light that's going into the space. So for the design of the pavilion, there will be a ramp that is like leading up to observation platform, and then there's this platform. The function is to actually allows the visitor to admire the big scale kind of sculpture at a nearer scale. So I will end my presentation with a bird's eye view of the entire site. This will be my last slide of the presentation. Thank you.
Ooh, thank you. Thank you so much for sharing.
Thank you.
I think we have a fan here first. Hi, Joey. Joey, you want to say something?
Oh my god, how is you yo?
It's good.
I didn't
I
know
didn't
you
expect
know after
you
I
to
came
be
in, I saw
here.
your face like, huh? It's you. Okay.
Let's
Yeah.
see. Thank you so much. You want to stop share? So maybe we can have a very fun and casual Q&A. Mehdi, what do you think?
That was very interesting, Jin Ting.
Oh, thank you.
A very good process. I could see how you could develop your design. I mean, I always tell my students here, you cannot design, for example, something with clay unless you touch clay. And I'm happy you did it before you start your design. It's the feeling of touching clay, touching the material, knowing how it works. It makes a huge difference.
Yes.
That was very interesting.
Thank you.
Nice. All right. Yeah, I have some questions on my side as well. I think I was wondering the same questions as Mehdi. I mean, I love the process. I love the entire concepts and the thinking behind, because I feel that there's a certain poetics inside when you mention this is a dragon clean, and then you design the backbone of the clean, and then all these individual modular cell, they are like the skin, and then you just cladder onto it, and then it's almost like a dragon flowing through the entire master plan. And I think that is actually very cool. You know, it forms a space, it's placemaking, but at the same time, it's also utilize the clay process.
Thank you.
But I have a question.
Yeah.
Like, given the chance that you have experienced the clay making yourself,
Mm-mm.
is there a reason, like, because you could have potentially designed the building using like the hand molding kind of technique, because the form will be completely different, like the one done by Anna Herringer, or like the kind of like ball, like more irregular shape as compared to this more sort of like an industrialized production kind of construction. So what makes you choose the first one?
Because I guess because if I really wish to like make it into a real thing to happen, I need to also consider some like how to really make it in real life, you know. Like of course hand making is always like very interesting and I really like it.
But
I
Singapore
guess
cannot do it, right?
yes, but I guess I was like a half practical and then half emotional person. So I also like will also question myself, oh, what if like I really want to use this like to actually produce more of this product. So actually I want to take in some of the production consideration into it lah. Yeah.
I see. Will you consider yourself as in like it's quite ambitious to use a clay as a building material? Because I think in the Singapore context, currently there's actually no building in Singapore who's actually using like raw clay or raw brick, right? There are like there's so many rules and regulations governized over like using concrete with plaster and waterproofing, etc. Do you think you see the potential in that, like in using that in more projects?
Yeah, I think now majority of the building are made by concrete in Singapore, and also there is like a small amount of like timber building which they only just started to explore like recently. And I know like Singapore is like always like looking for alternative material. So if Singapore already have so much of like excavated soil, so why not, right? Because there are always like a lot of ongoing um um how to say ongoing
R&D research and development.
R&D like land making new land at the shores and stuff. So there's always like this and also always there's this like underground development, and Singapore actually has this like underground master plan that there's like done by URA. So I see like there will be this abundant material that we actually should utilize. Like we shouldn't just like ignore the fact that we actually have a lot of this material and then just like keep importing things that we don't have from other countries.
I see. You're saying that like those clay can be obtained on underground?
Yeah, because clay is basically come from soil.
I see. Sorry, I mean, maybe just clarify, like, all this clay that can be anything from the ground. Like right now, I walk out from my house, the clay that I step on the ground, they can be used as a building material, or it need to be like a special composite inside.
I would think it also depends on like which type of soil that you are digging from the ground outside. Yeah, but in Singapore, the Jurong soil is actually quite famous for making pottery because of the high amount of this clay in this soil. So it was somehow you need to see the composition of the like different ingredients in the soil. Like it's not like any soil will do. But
I see.
Yeah, I think there is still like amount I mean what to say you still because the soil still contains a certain amount of clay. So I think after some of the processes, you still have the opportunity to make it into like clay.
I see. Because that also related to the question in the group chat was asking that is clay recyclable, or can it be like recycled or depleted into the soil? So the question, the answer should be yes, right? Since we are just getting it from the ground.
Yes.
I see. Okay, that's nice.
Let me add something here.
Yeah.
Clay is very fragile. When you make it, it's very fragile until you fire it. And when you fire it, it becomes ceramic. Those are two different names we use for that. And the composite of the clay, we have different types of clays. For example, we have earthenware, we have terracotta, we have different types of based on the composite, and composites that are in the clay. So when you fire the clay, it becomes ceramic. It is not recyclable anymore. Before that, whatever you do with it, it is recyclable until you fire it.
I see. So like, for example, terracotta is considered fired, right? And then you can't recycle it anymore?
Yeah, we still have some clay, raw clay. It's called terracotta. It's the, for example, the reddish color, maybe more brown because of the iron composite inside it. It makes the color different. But after that, when you put it in the kiln, it is not recyclable anymore.
Ah, I see. So it will eventually go to, I see,
I'm sorry, when I say it's not recyclable, you cannot leave it in the nature. You need to break it down. For example, how they do it, they break it down in small particles, and they add it, for example, to raw clay. They call it krog. It kind of improve, like the aggregates that you add to concrete. These are kind of the aggregates you can add to the clay and kind of increase the strength. How much, we should talk about that part. But this is how they recycle it. If we can call this part recycling, yes, this is how they recycle it. But if you want to leave it in the nature, no, it will never get back to the cycle of the nature.
I see. Ivanka, you want to ask something? You want to unmute yourself?
No, I think he just answered me because I was trying to understand like the nature of recycling altogether for clay. So yeah, so I was wondering, so does that mean that the only way is actually to reuse instead of recycle it as like aggregates?
That's true.
So he was just answering what I just asked.
I see. Got it. Okay, got it. Well, I guess there's different way, because later on I think Mehdi is gonna share about the 3D part and also 3D printing the clay without using any structural. So in a way that yours process doesn't require any firing, but then it has its own structural integrity. Am I right?
Somehow, yes. I will talk about the research we're developing. So we are adding some chemical additives to the clay. We're not firing it necessarily. We're adding some chemicals that makes it more strong. I'll talk about it in a bit.
Okay, cool. Yep. So I think on my side, I don't have any more questions. If the rest have anything to add? No? Okay, that's great. But I think thinking your project is very inspiring. I feel like the use of clay add depth to the entire program of the space, because it's very poetic. And then I like the cell that you make for each module. And then when you put together, it's almost like you customize the tiles, and then when it joins together, it has different programs and meaning. Thank you.
Thank you.
Do you have any final words to add?
Just to thank everyone that takes time to listen to this presentation. And if there is like some parts that I wasn't like explaining very clear, like feel free to ask in the chat. I think I can reply in the chat as well.
Woohoo!
Thank you.
Yay! So now, without further ado, Mehdi, it's your show, it's your stage.
Thank you.
Oh, sorry. Before I go to that, Jin Ting, your project wasn't published anywhere else on the website, because I cannot find it actually.
I guess it's only on my school's website.
Okay. Because PEM, the PEM website, they didn't even put up a proper image and description of the project. So if you don't mind, you can just share in your group so you can have a look. Thank you. Sorry.
You may share the images.
The link, if you publish it elsewhere. Sure. Thank you.
Sure, let me see.
Okay. Hello, everyone, again. And thank you, Jin Ting, for your beautiful presentation, beautiful graphics, beautiful narratives. Today, I just want to share a little bit of my research, what we're doing here. It might be a little surprising for young architects. This is very different aspect of the architecture I'm working on. It might look like a little boring, but let's see, I will walk you through it. But a little bit about myself. My name is Mehdi Farahbakhsh. I'm by heart an architect. Now I'm a researcher. I'm a PhD candidate here at Texas A&M University, and also a Center for Infrastructure and Renewal. I have some projects that I can talk about, but we're not here today to talk about them. So I will just jump into the research and why we are doing it. When we talk about or think about the future of architecture, we can define a range. And sometimes I personally feel insecure about the future. Which direction are we heading? When we think about the AI emerging in the design side, computers or AI, artificial intelligence, is the place of architects by designing more optimized productive designs. I'm not talking about the very artistic side yet, but it can be very soon, trust me. And the other side, when robots are coming into the field of fabrication, where are we standing as a new graduate student, as a new young architect? Where are we standing here? Are we following the traditional way of design or traditional fabrication or construction process? What is the future, and how far is the future? The future is next year. I'm talking about AI taking over our job, or it's about 10 years from now. There are a lot of debates in that part, but I really want to emphasize on this part. A lot of people are saying, or we used to say, if robots come into the field, if computer comes into the field, we will lose our job. We will take jobs from people, but I think that's not true. Computer entered to a lot of fields, but jobs evolved, improved, changed during the time. We never, for example, had a data scientist. Now we have data scientists. We have app developers. So the nature of the jobs will change during the time. And again, as a young architect or graduate student, I think you should think about your future, how you want to adapt yourself with all changing future of the field. But let me also talk about other aspects. We are concerned about climate change. We're concerned about the new technology, material breakthroughs, what's happening. For example, in terms of climate change, they're saying 38%, that's a huge number of global emission is related to building and construction industry. That's a huge number we're talking about. And 8% of that, of the CO2 emission is related to the concrete industries. So we are thinking, we should think about a replacement for concrete. I think Jin Ting mentioned that, for example, concrete and clay type of materials, they are good in compression, but they're not good in tension. What should we do? How we can replace those? Concrete is very difficult to replace, but how we can come up with that? On the other side, we have some technology and material breakthroughs, opportunities and challenges of using local material. You can find, for example, clay almost anywhere on the earth. You just need to remove the 30 or 1 foot of the surface. After that, usually you can find some kind of clay that you can use. So you can extract your material from the site and build something out of it. There are 4D improvements predicted by Smithsonian Magazine for the next 40 years. They're predicting that clay would be major material for the future. Sophisticated buildings in the future will be made out of mud. Additive manufacturing with clay that we have developed in our research group is actually based on an interdisciplinary research between architecture department, chemistry, civil engineering, and soil and crop science. So it is very interdisciplinary field. It is not just architecture thinking about design part. So the nature of the research has changed a lot here. And if you want, you can take a look at our publications and some interviews we had. You can take a look at it later if you want. If I want to focus on this, part in this multidisciplinary research, I can divide it into 3 different scales: microscale, mesoscale, and macroscale. Microscale is more related to material parameters in the molecule level. And this part is mostly the area of focus of my colleagues in chemistry, civil engineering, and soil and crop department. I, as an architect, have more focused on the mesoscale and macroscale. Mesoscale is more about the 3D printing process parameters. I will talk about them in a bit. And macroscale, which is more about the geometry of the form, how we can contribute to this research. When I talk about, this is the focus of area. When I talk about the meso and macro scale, why I'm focusing on that part, I, as an architect, do not have the knowledge to add to the, for example, the material properties. For example, if I want to replace concrete, if the goal is replacing concrete with some clay-based material, my colleagues are working on the micro scale, but I am trying to think, okay, let's say we have a material weaker than concrete. How geometry can help us to improve that? We architects are good at geometry and the shapes, how we can contribute to this field of research. When I talk about mesoscale, I'm talking about the bond strengths between layers, for example, here. And you know, by definition, additive manufacturing is depositing material layer by layer to create a form. And macro scale is the geometry of the whole shape of the form that you can see here. Based on that, we have developed some process parameters, 8 different process parameters that we are using a robot. Not necessarily, I don't call it 3D printer. We are using a robot in our research for some reason. I will mention it to you. And we just focus in this research because there are a lot of precedent research in this field. We're not the first group who are working on that, but we just focused on 3 specific parameters that I will talk about it in a bit. Why we're using the robot is because the robot has 6 axes, while normal 3D printers, they have 3 axes. They just move in X, Y, and Z direction. Robot moves in X, Y, Z direction and rotates along X, rotates along Y, and rotates along Z axis. So it gives a 6 degree of freedom. How we can use it, I will talk about it again in a bit. Robots have a lot of application nowadays in the field of architectural fabrication. If they can be used, as you can see, in 4, I can categorize them in 4 different groups: additive manufacturing, hot wire cutting to create a mold or something like that, assembly, or pick and place. My focus in this presentation and this research is additive manufacturing, using a robot for that purpose. We have developed some courses here to make our students familiar with the process of using a robot in the fabrication process. And the purpose is, again, to bridge the gap between the design and fabrication. We don't need anybody else. If we know code, if we know design, if we know programming, and if we know material. So we're bridging the gap. We're removing all the middle connection, middlemen here. So this particular one, we had explored different approaches with manipulation, with casting, with hot wire cutting in this specific course. And in the other one, we called it not just the brick in the wall. So we had some components designed for a building facade. For example, you can see these could be used as a facade, and they were all 3D printed, and they came out of a design process that our students initiated at the beginning of the semester. It might be interpreted similar to what Jin Ting was trying to achieve, but with limited components. As you can see on the very left at the bottom. You can see here, I don't know if you can see my the cursor on the screen, or should I use the, okay, if you can see it, that's good.
Yes,
yeah,
you can see the cursor.
Great. So if you pay attention to the color of the clay, it's kind of gray, and it is still wet. When you let it dry after a couple of days, it becomes, it's light gray. And when you fire it, it becomes based on the clay you're using. For example, here we were using different type of earthenware, and here we're using, for example, white clay. It's called, after firing, it changes the color. And it is very, as you can see, it's very, I don't know how to call it. It is soothing for me, but it might be messy for them. They were complaining a lot, students were complaining a lot, because it was mass production. It was not just one piece. We had many pieces. So it is not just, at the moment, it is collaboration between human and robot. It's not just you push the button, enter, and robot builds this structure for you. No, it's still in the process of development. So a lot of human interactions and human labor should be used in this process here. In the next project we had, it was last semester. Yeah, it was last semester. We had optimization of a column. So students were designing a column, and they were focusing on how to optimize the design of the column. And then they were producing, or they were fabricating their designs. And in this one, you can see it was, the question was like, how we can build a structure which is larger than the scale of the robot. If we have a robot or 3D printer, are we always limited or bound to the scale of the robot? Can we build something like in the scale, larger scale that Jin Ting was talking about it? Here we are talking about print in print technique. So based on the geometry that you develop, you can stack stuff into each other, and then you can take them apart and put them on top of each other, and finally you can build a structure like this. Or in this current one, this project was done this semester, and just yesterday they finished the installation. I have some pictures, but not all of it. Again, the design, the question was like, how we can print a structure which is small, which is reachable for the robot, but then later we can assemble it in a larger scale. And these are some samples, these are some pictures of the initial process. As you can see, they focused on the joints, how they can attach these pieces together, and how they can print them on a stack, and later disassemble it and make a larger structure. Let me go to the programming part. I will get back to the main question of the research, and I will explain it to you. So in terms of programming in the future, if you don't know programming, you're kind of illiterate. It's not just knowing the writing in English or any languages. It's not what makes you educated. If you don't know the programming, somehow the basic of programming, you might have some problem. For example, here in this courses that we teach here, we are focusing on offline programming, that you program everything beforehand, you send it to the robot, and robot executes it. But we have some real-time programming as well, that you collaborate, the designer collaborates with the robot in the real time, and robot responds to the changes based on the situation, based on the feeling of the designer or whatever. We have different types of robot that I will skip here, not explain a lot. And this is the workflow that if you want to control a robot, you need to know that. Very, very basic and fundamental way of controlling a robot is robot operation system, ROS. A lot of people in computer science are using that part. Also, you can use another software developed, for example, by this brand of robot, ABB. You can use Robot Studio, but we as designers are more focused on visual programming. It's much easier to use visual programming. For example, example, like Grasshopper, which is a plugin running on Rhino. And there are other plugins using, for example, How or Machina to control a robot. Let's get back to the main question of the research, how we can use the robot, a 6-axis robot, to print structures. Why I'm focusing on 6-axis of the robot? Because the 6th degree of freedom that a 6-axis robot gives us, we can follow the path of the forces in a form. And I will show you in a second. Almost all the 3D printers, most of the 3D printers available in the market, they are, even this one, for example, a space nozzle is always perpendicular to the surface. As you can see, they are always facing down. In normal 3D printing with plastic, it's always like that. But when you use, when you want to make something scaffold free without any additional support, you need to follow the path of the loads inside the form. And while you know the geometry, if you want to print a vertical wall, all the layers are perpendicular to the print bed. But when you want to print an inclined surface, one way is corbelling system, that you shift the top layer a little bit from the bottom one, and you print a inclined surface. But the other way, when you use a robot, a 6-axis robot with 6 degrees of freedom, you can change the angle of the nozzle and you can follow the path of the loads inside the surface. So later, when you have a curved surface, you can print a curved surface if you change the angle of the nozzle. That helps us to print some organic forms like this, which they are scaffold free again. You don't need additional support to print this structure if you're using if you're changing the angle of the nozzle when you are applying the force. For example, here, maybe I can draw something on it. Here, the nozzle can be facing this way, but when you go there, the angle of the nozzle should change. Here, the angle of the nozzle should change to follow the path, the path of the load in this structure. This is one, the small prototype that we printed here without any additional support again. And we focused on 3 parameters in this research, how we can change, for example, the height. It's called the standoff distance between the nozzle and the print surface. How does that affect the print? How can we improve that part? By changing, for example, it's called H2. What if we change the H2? Can we change the bond strength between layers? When I'm talking about changing H2, for example, here H1 is the thickness of the layer, and H2 is the standoff of the nozzle and the print surface. By just changing that H2, you can see we can get a kind of bumped or diamond pattern here, and it improves the bond strength between layers. It's something beyond or different from the micro scale. This is happening in mesoscale, as I mentioned. And just by changing H2 parameter among all 8 parameters that I have already introduced, we will get different results. By just changing one parameter, we'll get, for example, here H2 is 6 millimeter, here H2 is 20 millimeter. Here is like you're making knots inside the layering. And then we applied that in many geometries. We're applying that mesoscale in macro scale, which is the geometry of the form. And then you can print geometries which are more complex. For example, we're trying to print a dome-like shape. And we came up with different patterns that based on the design, based on the forces that are being applied to the form, we can use one of those or a combination of those. This is another workflow that we evaluate those claims. So we have claimed we're improving the bond strengths between layers. How we can prove it? In architecture, we are saying, okay, that's fine, we have improved, but we need numbers, we need science behind it. We need to back up it with scientific results. That's why this part we're calling it design, that we generate the parametric geometry and we program it. Then we have the fabrication step that we build the geometry. Then we need to analyze it. For analysis part, we need to reconstruct the digital model made out of the physical model that we printed here. So we have a printed object here. We, using X-ray technology and digital image processing, we are reproducing the model, and then with numerical simulation, you're analyzing it. This is, for example, one example how we prepared our samples, different layerings, and then we put in an MRI machine to reconstruct the digital model, how you can see it here. So because in the initial digital model that we designed the parametric geometry, we don't see environmental stimuli as it is in the environment. It's temperature, humidity, pressure of the nozzle, material properties. Some of them, they could be included in the initial model, but not all of them. So that's the reason we print them, we re-scan them, and then we do some physical and digital analysis on it. For example, this one is how we break those samples and get a library that gives us the parameters of each model. I know it's too theoretical. I don't want to bother you and make you more tired than I did before. So in the process, I'm just here want to explain to you. When I started this research, there was no industrial, for example, extruder to be used with the robot, to be used with this machine we had. So we needed to design and develop our own tool. As you can see, this is also part of the process. In my classes that I teach here with my students, I am asking them, you need to develop your own end effector, your own tool if you want to do something. For example, we saw in Jin Ting's presentation, she developed her own mold or 3D printed mold, and then she casted it. It is exactly part of the process. You as a designer nowadays need to think about all aspects of your design. So for example, here from the initial extruder, very basic one, we came up with the more advanced one that we had a microcontroller, we had more control over the flow of the material. I'll show you. This is the first one. We could just extrude some material, and later with more control, we could come up with more controllable flow, controllable process, and we could make some geometries like that. Again, we developed all aspects of the design. These are the parts have been designed by architects, unfortunately, not engineers exactly. And you need to deal with a lot of failures. The left side is all our failures. For example, we designed some augers, it didn't work. We needed to study what is auger, how does that work? These are all aspects we needed to work on, and we also programmed the microcontroller, as you can see it here. And that's it.
Thank you.
You're welcome.
Wow. For the record, I personally think it was quite interesting. I don't think it's boring, like keep mentioning it. Yeah. Jing Ting, you want to say anything in the beginning before we start? Okay.
Yeah. So I'm really intrigued by like using the 3D printing this method to create like clay structures, especially like not only just like to explore the wall, you also explore the column. And I also really like this texture, the kind of 3D printed texture. And then I feel that it's like kind of like a new expression for clay material. And also I also really like that these are actually like based on the study on how the nozzle was, like on a different speed and on different distance, and created this like different texture that is like really looking very beautiful. Yes. And also I'm very amazed that and you really go down to the detail of designing the extruder for the 3D printing. Yeah, it's really, really inspiring.
Thank you. Yes, that's a good point. I mean, improving the conventional pottery, or maybe convention, I don't like to call it pottery because it's not necessarily pottery. We're making spaces. We are still in a small scale, but eventually we will scale up into the largest scale. In the 3D printing industry, nobody likes that layering, that horizontal layering. They're thinking, I mean, they're thinking, always arguing how we can cover that. It's not beautiful, how we should cover it. No, it can be beautiful if you just change the pattern. It's not always horizontal, sometimes based on your form. This is where architects and designers comes in, can show their role, can play their role. Either it is interior designer or it is an architect. They can come to the play and say, okay, 3D printing and that layering can be beautiful if you know how to use it.
Extruder.
Sorry, I didn't hear you.
Oh no, you're talking about the layering of the 3D printing. So I was thinking that, was it because you can actually amend the extruder, so when you print out, it's actually a very beautiful layering than the general layer thing that we see. I never done I never done the additive manufacturing before, so sorry in advance if I've asked any stupid questions. So I was just wondering, like the robot, where do we stand at the moment at this technology advancement? Because at this point we are still doing all this research and development. But how long do you think, or is already in the process that this is actually can be employed in the construction, in the current construction world? This technology.
A lot of groups, either research group or practice, they're applying this technique, this technology into the real size structures. There are some groups in Eindhoven, ETH Zurich. Here in Austin, we have some companies they're applying that, but the problem is they do not comply with the building codes yet. Not all of them.
So they are large scale building, like still multi-stories.
So that's a different story. We have 2-story buildings at the moment, not more than that yet. Because it's very difficult how you want to add another technology, how you want to do the roof, the ceilings. Again, printing vertical surface, it's not a big deal. But when you want to do horizontals, you need to use either another technology or you need to print it somewhere else and use a crane, put it in the precast, prefabricated, and put it in a place. That's why we are working in this. How we can create something which is not vertical, which is inclined, which is more organic shape. And
the
also,
robotic arm comes in with the whatever rotations of the extrusion.
Right. Or some people are doing research on how they can employ drones to deposit material. But drone is different because they cannot carry a lot of load. How we can solve that problem? My point here is the aesthetic, we are used to 90 degrees in the building. We want everything to be square. Sometimes we want the roof always be, how we call it, perpendicular, for example, to the columns. But maybe we're moving to the era that if we want to use clay, we need to get used to more organic forms. The aesthetic of the forms shouldn't be always 90 degrees. I saw that in Jin Ting's design.
Yeah, at least Jin Ting design is 90 degrees.
Yeah, a lot of curvatures.
Yeah.
How we want to deal with the floors, with the roof. The roof is always flat, not necessarily, but that's where architects need to step in to the process.
Agree. that brings me to the next question. So like Jin Ting's way of constructing her design earlier on, she was mentioning using slip casting, which is have a special mold, and then you just prefab everything, and then you have this all come in by pieces, and then you install it. I mean, I'm just wondering in terms of, because one of your slides was showing that this robotic arm was actually doing the same modular thing, and then after that you stack them together. I was just wondering, if it's the same outcome, will the slip casting will achieve much more efficiency than the robotic printing? What is the benefit that robotic printing compared to other methods? I mean, except for the form that we mentioned earlier.
That's a good question. We can sometimes we can achieve with we can create some very complex shapes in ceramic or in ceramic industry. Like for example, you have paid attention to the toilets. They're all ceramic, but it has very complex shape. The way they are making it, they have a mold and they have a liquid that they inject it, then they remove it, they have a thickness of that. But again, when we are talking about buildings, the scale is much more different. You cannot spin the whole building to make that complexity. With 3D printing, we're able to create complex geometries in a way that they are reliable in terms of structure, if that makes sense.
I see. I think it makes sense. I think from another point of view, the 3D printing, it combines both, how to say, the labor and the material itself, whereas the slip casting, on the other hand, it's only the material. And I feel there's much more limitation to the form, like you mentioned earlier.
That's true. That's true. But I would not put all the responsibility to the robots yet. It is still in the process of human-robot collaboration. Still, again, I remember, I can't remember his name. He is responsible for Toyota's AI lab or something like that. They're working with Atlas robot, for example, a lot of advanced robots. He was saying, robot in the lab, it's always broken, sitting next somewhere in the lab, and you are human are doing the labor. It was like, I was watching, robot is sitting there watching us when we're doing all the labor. For now, it is like that, but I hope in the future, the labor is done by the robots.
Which is going to be, isn't it?
I hope so.
Okay, I think Ivanka has a question, so maybe you can. Hi, you want to just unmute yourself and ask?
Hi, no, I'm just wondering, like, in terms of like a clay printed wall, like, how does it stand against the average concrete wall? Because I think you started your research based on the fact that like we are using concrete, like, is it replaceable, right? Something along those lines. And like, I'm just wondering, like, because I was very intrigued by one of the slides that you shared. It's the vertically printed in situ walls and columns, the one that's in US, really big with a lintel one.
By Andre Ludenko.
Yeah, we're just wondering, like, how does that work, and like in terms of versus a normal wall, did it actually solve the issue of like the tensile strength and all that? Like, did it meet the basic requirement of like how a concrete wall would stand?
Yeah, sorry, maybe I can add on, like, I wonder the performance in speaking of thermal insulation part, and the property is definitely kind of different from the red clay or sand brick. Yeah, I wonder, how do you see that performance in this sense?
In terms of thermal, you said? In thermal
insulation?
Thermal
insulation, yeah.
So there are like two questions, like one is the strength and then the thermal. Summarize.
Should we ask Ayayushi come in? I'm just joking.
So first of all,
yeah,
we're still far from the strengths that concrete can give us. That's why we're doing some geometry investigations, how we can change the geometry of the form to improve the strengths. We cannot achieve the strengths of the concrete.
So using engineering, like.
Yes. And for example, sometimes we need to have more thickness compared to concrete. When we're using, for example, clay or clay-based material, we need more thickness of the wall to get the same strength. But still, it doesn't comply with the code. And there is a very strict regulations on buildings with clay here in the US. If you know Hassan Fathi, he was a famous architect using clay. And he had a lot of problems. While he was working outside of the US, he was in Egypt, I guess. He had a lot of achievements. But when he came to the US, he was spending a lot of time just dealing with the building codes. So he was very limited. Again, we're still far from concrete, and all the research is in that direction. Ayushi's team, who we are working with, they're chemists. They're using on some additives, how we can add some additives to the clay, so we can use, for example, local material that we extract from the site and make it to the reliable material for the building. We're still far from that, unfortunately. And in terms of thermal insulation, so there are some technologies that you can, while you're printing, you can add insulation in forms of foam or something between the layers of the wall. So you can add some thermal insulation, but we need some, for example, if you look at the traditional buildings and compare it to the new buildings, which are very thin, we don't have thermal capacity, which, for example, if you run AC for a couple hours and you turn off AC, the modern building, which have very good insulation, but they don't have enough thermal capacity, they will lose heat very faster than traditional buildings. So we need some of that thermal capacity in the buildings that you can achieve with either concrete or clay-based materials.
I wonder, when the 3D printer does the job, do they leave like an air gap in a way? You know, it's pretty much similar to, you know, the traditional way that they usually have leave this kind of air, you know, like I don't know, like perhaps like 2 or 3 inches of air, like a gap to allow the temperature to pass through or transmit this kind of heat. So perhaps this is something, I don't know, because I saw most of the 3D printed images that you shared is really nice in a way. They allow this kind of grid, like a crisscrossing in between the wall. So I also thought that might be perform the similar things or effect.
It's almost similar. Yes, you're right. It's almost similar.
Cool. Thanks a lot.
Hi, Mehdi. Thank you for the sharing. Like, I'm excited for what you have done. Like, I take this as sort of like a work in progress, right? I mean, yeah. So I mean, I had this question, like, do you think using robots and computational systems could optimize the material usage as well? Because we are maximizing the tolerance of the material itself. So meaning we also can reduce the reliance on resources, right? Isn't it? Do you think?
Absolutely, that's the point. So we have a term called embedded energy. While we are using, for example, steel, we are using a lot of energy to extract and make that profile, that steel. That's kind of using some resources. That's some kind of energy resources. But while you're using, for example, local material, you're removing the transportation, the initial investment for using the material. It's not just the amount of material that you're using, you know? That's a very good point. We are hoping with using local materials like that, we are removing a little bit, as much as we can, the embedded energy or their usage of resources.
Yeah, and I also see that sort of you know, like recently there's a search of it's called a discrete architecture that, you know, it's discrete. I mean, like the thing you print, you know, like it's being printed in a well-latticed way, meaning we don't need to build the whole structural load as a whole slab anymore. We can look at it as sort of like a more permeable structures right now. That I see there's a kind of reductions on material that we're going to use for the whole thing. I mean, a perception to it. Yeah.
Yeah, I'm familiar with that discrete kind of design they're doing. I don't call our approach, which is print in print, or the other one is nested printing that I showed you. We don't call that discrete, but they have similar approaches that you can print in a smaller stack, and then assemble a larger scale structure.
All right.
Well, I hope your questions are answered. Yeah, thank you, Mehdi.
You're welcome.
I think I have maybe one last questions to conclude the sharing. If anyone has any last question, you can post in the chat as well. So I know Mehdi through Miss Ayayushi, which is a presenter in Narratives of Soy Forum organized by Wendy. So it was also by chance that I saw her research. So she is a chemical researcher in the same university that Mehdi was studying in. So my question would be like, how does your collaboration with Miss Ayushi comes about, and what is the dynamic in this sort of working relationship? Because what I'm seeing is, I mean, there's definitely research and development in the material side, but it's always the work of the researcher and the designers always silos. I mean, there's always a disparity. Like we don't know. I mean, we designers is still designing using the conventional methods, traditional material, where there is such a great research done there. So how do you see we can improve this, and also maybe use your working relationship with Ms. Ayushi an example and inspire?
Yeah, that was a very valuable experience. It was not easy because we were speaking different languages. They are speaking of science. We were speaking of philosophy, beauty, aesthetic, those sort of stuff. It was very beautiful to align those different approaches, and it was not easy. But the result is really satisfying when you understand finally, you understand as a designer, you understand the language of scientists, how you can change or optimize your design, as Joanne was talking about, how we can optimize the design to comply or to remove some excessive usage of material, smart use of material. You can see in the work of a lot of researchers, they call it smart materials, how we can align that part. It just needs more study and research in the field of scientific aspect of the field. When you're looking from outside, they call architects are just thinking about the beauty of the aesthetic of their design. It's not true, because now if you do not update yourself with all improvements in terms of material technology, AI, all of that, you're far behind. And how we collaborated, it was we had different sessions talking about our requirements. She was talking, for example, Ayushi was talking about what they like to achieve and how we can implement that part. And how, for example, my concerns was scaffold-free, optimized geometry, bond strengths between layers. And she was thinking about micro scale, which is
molecules. I remember
molecules.
Yeah, I see.
That's very interesting, but not always easy.
I'm just wondering, does the school play any parts in it? As in, like, they must be require you guys collaborate with any other researchers, or it's just purely by self-initiative that you guys find each other to collaborate?
So it started with a grant that university allocate to the multidisciplinary research groups. So
Wow.
initially it was the money. They were like, okay, you have this much money if you collaborate with others. So there are a lot of teams apply for that. Our team proposed what we want to achieve, and they granted the money. Other than that, we could do nothing. So the money was kind of the initiative.
I see.
There is a lot of it. Texas A&M is, I guess, this year it was the biggest university in the U.S., the largest university in the U.S. So they have some resources, they have some money, but there is very competitive. It's very competitive to get it.
I see. That's great. Congrats that you guys get it. You guys get it, right?
Yeah.
Got it. Okay. Well, thank you. I guess one last question is: do you think the wonderful patterns of all the geometry just now you have mentioned, are they available in the library for public, or they are within the school property?
No, we have published some of our work. I mean, I shared that if you go back to the video, there is a QR. No, there's not a QR scan code, but you can just Google the name of the research. I think we have 3, maybe 4 papers right now. I shared in the first or second slide. If you go back and you look at it, you can find some of our research.
The QR code or the website, is it?
Yeah, the QR code is, I guess, just the interviews. It's not very informative. It is more for general audience. But if you want to go more in depth, there's some publications in Acadia, which is the
paper
most reputable. It's the most reputable computational design conference in the North America. You can find it there.
Awesome.
They're full of wonderful stuff. I even like the place you do your research, like Texas, like I always refer to their stuff as well. I mean, like they're full of like computational and fabrication.
I see.
Yeah, it's tons of it. Yeah, especially Acadia. They do not even physical, they do digital architecture as well. Right?
I see.
Yeah.
That's so cool.
Yeah.
It's nice. Well, I'm just wondering, in Malaysia or Singapore context, do we have this machine here?
No, Malaysia. So far.
So far, no, right?
No, there's no KUKA in any national U.
Oh no, so sad.
I know some people I'm not sure if they're in Hong Kong or if they're in Singapore. I don't know. But there are very good researchers over there. I know they're working on architecture side.
Yeah, I think it's Singapore and Hong Kong. SUTD, they have a machine, and Hong Kong U does as one.
As in the SUTD has the machine?
Yeah,
or like do the research?
Yeah,
I see.
Yeah.
Jin Ting, SUTD got the machine.
SUTD does like digital fabrication, like crazy.
Why you didn't go and knock the door?
How? Yeah, ask my school, but I couldn't find it in my school, so maybe I go to the wrong school, is it?
Yeah, competitors.
They need to grant, like you give the grant for cross-school collaborations.
Yeah, because I think like SUTD are collaborating with MIT. Yeah, so I think they have more resources in terms of.
See, I think Lit say that NUS ETH lab has it, but architectural students are not allowed to access. Lit is from Singapore as well?
But their 3D print clay is like kind of a bit different from what we did. Like what Mehdi did. It's more like for the medical use kind of thing. It's like it won't look like clay. It still look like it's like another kind of thing. Yeah.
Is the bio material sort because it's medical?
Yeah, it's quite it's really like engineering driven kind of for like usage in a medical like in operations.
I see.
Yeah. Thank you.
All right. Thank you, guys. I hope you guys find today's sharing informative. And if you wish to contact the speakers, feel free. I think their emails is available. You guys can tap in the chat if you guys want your email to share. And then I guess that's it. Hope you guys enjoyed it. And let's take a group Zoom fee, I guess, and then we shall end the session. All right, you can turn on your camera if you wish to, and then we'll take the Zoom fee in 3, 2, 1. Wait. 3, 2, 1, smile. Okay, great. Thank you, guys. Good night and good morning. See you next time.